the little fix for big O. Thankfully, there's an easy way to eliminate all these extra recursive calls. We'll call max only once within our code and save the result to our variable. So the fix to the recursive call or multiple recursive call, which is a problem we encountered previously, is storing it in a variable. So we will see how this one technique of storing in variable will enormously or delete all those recursive steps. So here we define max again with a parameter array, return array index 0 if array.length is equals to 1. Calculate the max of the remainder of the array and store it inside a variable. So here we are gonna calculate the max of the array. It's still the same recursion comparison of first number against this variable. If array index 0 is greater than max underscore of underscore remainder, so we store that in a variable, return an array index 0, else return max underscore of underscore remainder. So we use this max underscore of underscore remainder and the index 0, and then we compare that. So we used comparison and if statement and delete all those extra line of code and extra recursive calls. By implementing this simple modification, we end up calling max a mere 4 times. Try it out yourself by adding the puts recursion line and running the code. The trick here is that we're making each necessary function call once and saving the result in a variable so that we don't have to ever call that function again. Again, the trick here is that we're making each necessary function call once and saving the result in a variable so that we don't have to ever call that function again. So here we store that max remainder to a variable so that we don't need to call this function again. So that's actually the key for this variable. The efficiency of recursion. In our second improved version of the max function, the function recursively calls itself as many times as there are values in the array. We'd call this on. Up until this point, the cases of on we've seen involve loops, with the loop running n times. However, we can apply the same principles of big O to recursion as well. Since the improved max function run n times for n values in the array, it has a time complexity of on. Even if the function itself contains multiple steps, such as 5, its time complexity would be O5 times n, which is reduced to on. So in our second improved version, the max function, the function recursively calls itself as many times as there are values in the array. So this function only call, since we store that in a variable, only call as many values or elements in the variable. We'd call this on. Up until this point, the cases of on we've seen involve loops. So in the previous examples, it involves loop, which with a loop running n times, so it becomes n squared. However, we can apply the same principles of big O to recursion as well. Since the improved max function run n times for n values in the array, it has a time complexity of on only. So here we significantly reduce that from n squared to on. So the following to 5n rather. The following table show how many steps max gets called on arrays of various sizes. For 1 is 1, 2 is 3, 3 is 7, 4 is 15, 5 is 31. Can you see the pattern? When we increase the data by 1, we roughly double the number of steps the algorithm takes. As you learned by our discussion of the password cracker on page 107, this is a pattern of O 2 times n. We already know that this is extremely 2 raised to n rather. It is not 2 raised to n. we already know that this is an extremely slow algorithm. The improved version of the max function, however, only calls max for as many elements as there are inside the array. This means that our second max function has an efficiency of on instead of 2 raised to n. This is a powerful lesson. Avoiding extra recursive call is key to keeping recursion fast. What at first glance was a very small change to our code, the mere storing of a computation in a variable, ended up changing the speed of our function from O 2 raised to n to on. Excuse me. Overlapping subproblems. The Fibonacci sequence is a mathematical sequence of a number that goes like this until infinity. 0, 1, 1, 2, 3, 5. So it essentially adds the previous number. So like here, 0 plus 1 plus 1 plus 2 equals to 3 plus 3 plus 2 equals to 5, etc. So it's add previous two numbers. So this is the following Python function. Returns the nth number in the Fibonacci sequence. For example, if we pass the number 10 to the function, it will return 55, as 55 is the 10th number in the series. The 0 is considered the 0th number in the series. The key line in this function is return fib n minus 2 plus fib n minus 1, which sums the previous two numbers in the Fibonacci numbers. It's a beautiful recursive function. So here we define fib with the parameter n. The base case are the first two numbers in the series. So if n equals 0 or n equals to 1, return n. And if not, return the sum of the previous two Fibonacci number, n minus 2 plus n minus 1. So let's take a computation of the 6th Fibonacci number, for example. This function fib6 makes a call to both fib4 and fib5 as shown in the diagram. Here we call that fib4 and fib5 because it needs the previous two result of the function. As we've seen, calling a function calling itself twice can easily lead us down to 2 raised to n. Indeed, here are all the recursive calls made by 5, 6. So as you can see, 0, 1, 0, 1, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 9, 10, 10, 0, 1. Yeah, so it calls itself twice. So while one simple change worked to optimize the first example in this chapter, optimizing our Fibonacci sequence isn't as simple, and that's because there isn't just one single piece of data we can save in a variable. We need to calculate both fib n minus 2 and fib n minus 1, as each Fibonacci number is the sum of those two numbers, and storing the result of one won't alone give us the result for the other. This is a case of what computer scientists call overlapping subproblems. Let's unpack that term. So if we cannot store it in one variable, that's what computer scientists called overlapping subproblems, because we solved the subproblems using storing the value in the earlier example. And here, unfortunately, because there's two variables we need to save or to store, there's an overlapping subproblems. So when a problem is solved by solving smaller version of the same problem, the smaller problem is called a subproblem. The concept isn't new. We've been dealing with it frequently throughout our discussion of recursion. In the case of Fibonacci sequence, we compute each number by first computing the smaller numbers in the sequence. The computation of these smaller numbers are the subproblems. Since there's two subproblems, there's overlapping subproblems. Again, we have fib n minus 2 and fib n minus 1. What makes these subproblems overlapping though is the fact that fib n minus 2 and fib n minus 1 end up calling many of the same function as each other, that is fib n minus 1 ends up making some of the very same calculation previously made by fib n minus 2. For example, you can see in the previous diagram that both fib4 and fib5 call fib3 as well as many other duplicated calls. So how do we solve this problem? So enters dynamic programming through memoization. So luckily we do have option, and that is through something called dynamic programming. Dynamic programming is the process of optimizing recursive problems that have overlapping subproblems. The first technique is something called memoization. Essentially, memoization reduces recursive calls by remembering previously computed functions. In this respect, memoization really is like its similar sounding word, memorization. So it's like memorizing those previously called function or previously computed function, kind of like undo function, right, in the stock. But this memorization or dynamic programming really allows us to store those previously computed function to overcome those two variable storation problem that we encounter in overlapping subproblems. So let me just take a zip of my copy. In our Fibonacci example, the first time fib3 is called, the function does its computation and returns the number 2. So it's like here. However, before moving on, the function stores this result inside a hash table. So before it moves on, so since this dynamic programming essentially needs another parameter, which is a hash table, which store the previously computed function to this hash table before it moves on. So essentially storing those multiple variables. So the hash table will look something like this: 3:2. This indicates that result of fib3 is the number 2. Similarly, our code will memoize the result of all new computation it encounters. After encountering fib4, fib5, and fib6, for example, our hash table will look like this. So now that we have this hash table, we can use it to prevent future recursive calls. Here's the way it works. Without memoization, fib4 would normally call fib3 and fib2, which in turn make their own recursive calls. Now that we have this hash table, we can approach things differently. Instead of fib4 just blithely calling fib3, for example, it first checks the hash table. So that's the reason it first store or check this hash table before it moves on to the next compute, to see if the result of fib3 has already been computed. Only if the 3 is not in this hash table does the function proceed to call fib3. So only if the 3 is not in there, it will proceed with that compute of the fib3 or the next computation. So memoization goes for the jugular of overlapping subproblems. The whole issue with overlapping subproblems is that we end up computing the same recursive calls over and over again. With memoization, though, each time we make a new calculation, we store it in the hash table for future use. This way, we only make a calculation if it hadn't ever been made before. How does each recursive function gets access to this hash table? The answer is we pass the hash table. So how do we each recursive function get access to that hash table? The answer is we pass the hash table as a second parameter to the function, like what I've said. Because the hash table is a specific object in memory, we're able to pass it from one recursive call to the next. So because it's an object in memory, so here's the thing that we have not discussed in the previous video. A hash table is actually an object. It's just an object in memory, kind of like those object-oriented programming that has properties as well that help define the object. So hash table is also an object in memory, and we're able to pass it from one recursive call to the next because it's just an object in memory. So kind of like in stock as well, it's just in memory, but it allows you to undo the recent function even though we're modifying it as we go. This is true even as we unwind the call stack. Even though the hash table may have been empty when the original call was made, that same hash table can be full of data by the time the original call has finished executing. So it's kind of like in recursive, since we know that recursive function actually stem from stack, right? So this is true even if we unwind the call stack. Like even though the hash table may have been empty at first, but as we compute, the stack will keep growing because of that recursive call when the original call was made, and that same hash table can be full of data by the time the original call has finished executing. Implementing memoization. To pass the table along, we modify the function to accept two arguments with the hash table as the second. So we're gonna accept two arguments with the hash table as the second, and we'll call this hash table memo, as in the memoization. So these are the parameters end and memo. So when calling the function the first time, we pass in both the number and an empty hash table. So here fib 6, let's say we want to know the Fibonacci of 6. So these are the function that we want to compute, or the number, and we pass in both the number and an empty hash table. So we start with an empty hash table because again, along the compute, the stack will be poured into it, and after that, if you're computing like a 6, therefore that by the end of the function, those will be filled up with data with regards to this fib6 function. Now each time fib calls itself, it also passes along the hash table which gets filled up along the way. Here's the rest of the function. So here we define 5n and then comma memo. If n equal 0 or n equal to 1, return n. So these are the base case. So check the hash table called. So here's how we check the hash table called memo to see whether fib n was already computed or not. So if not, memo.get n. If n is not in memo, compute fib n with recursion and then store the result in the hash table. So this is how we store it in the hash table. So notice guys, here storing it in hash tables like storing that in the variable in the previous overlapping subproblems, but in this case it's just another parameter in another argument in our function. We also add that as an argument. Now by now, fib n's result is certainly in memo. Perhaps it was there before, or perhaps we just stored it there in the previous line of code, but it's certainly there now. So let's return it. Return memo n. So again, our function now accepts two parameters, namely n and the memo hash table. So here we could also have memo set to default value, just like in the recursive function where we store index 0, since we already know the end goal, that those 0 index is kind of like the base case, or the function will not go past that since it's the base case. But here we can also have the memo set to a default value, so we don't have to explicitly pass in an empty hash table the first time we call it. So instead of having the you or the customer have passed that empty hash table on the function, you can pass that on the memo as a value in the function to avoid so that the customer or you just need to pass the function you want to compute, or the value of the function you want to compute, such as in this case, which is fib6. So in any case, the base case of 0 and 1 remains the same, or unaffected by memoization. Before making any recursive calls, our code first checks to see whether fib n has already been calculated for given n. So if not, so before making recursive calls, this is the key code. Before making that recursive function, it checks first the memo if the value we're looking for is already there. So if not, memo.get n. So if the calculation for n is already in the hash table, we simply return the n. We simply return the result with return memo, and only if the calculation for n has not yet been made do we proceed with this calculation. Memo n. So as you can see, this is how we store the multiple previously compute function or variables to avoid this excessive recursive call. So here memo with the open and close square bracket with parameter n equals to fib n minus 2 comma memo plus fib n minus 1 comma memo. Here we store the result of the calculation in the memo hash table. So we store the result of the calculation in the memo hash table. So we never have to calculate it again. Also note how we pass memo along as an argument to the fib function each time we call it. This is the key to sharing the memo hash table across the calls to the fib function. Again, here we store the result of the calculation in the memo hash table of the function. Notice how this code does two things. It calculates the fib function or the recursive call while at the same time storing it in the hash table. We equate that so that we never have to calculate it again. Also note how we pass memo along as an argument. So here in this function or recursive function, we pass that as an argument to the fib function each time we call it. So that's another key line of code or word. This is the key to sharing the memo hash table across all the calls to the fib function. As you can see, the guts of the algorithm remains the same. We are still using recursion to solve our problem, as the computation of fib is still essentially fib n minus 2 plus fib n minus 1. However, if the number we're computing is new, we store the result in a hash table. And if the number we're computing was already computed once before, we simply grab the result from the hash table instead of computing it again. So, however, if the number we're computing is new, we store the result in a hash table. So if it's new, kind of like we're using an if-else statement. If it's new, we store that result in hash table. And if the number we're computing was already computed once before, we simply grab the result from the hash table instead of computing it again. So again, we're using if statement here. Another characteristics of this. When we map out the recursive calls in our memoized version, we get this graph or representation. So you can see here are where the square in this like a tree graph is where we get the result of fib from the memo or from the hash table. Fib 3, fib 2, fib 4 are never have to be calculated again. In this diagram, each call that is surrounded by a box is one in which the result was retrieved from the hash table. So what is the big O of our function now? Let's look at how many recursive calls we make for different types of n. We can see that for n, we make 2n minus 1 calls. So as you can see, for n, we make 2n minus 1 calls. So since big O, we drop that constant. This is an ON algorithm. So 2n minus 1 calls. So 2 times 6 equals to 12 minus 1 equals to 11. So you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So as you can see, we have 11 calls. So first call, and then second, third, fourth, fifth, sixth, etc. Right? So n elements 1, 6 equals to 11 calls. So 2n minus 1. So it's the another representation with regards to n elements and its number of calls. So dynamic programming So this we'd reduce that from 2 raised to n to an on essentially, or 2n minus 1 calls. So that's how we reduce that Fibonacci function. So dynamic programming through going bottom up. The second technique, known as going bottom up, is a lot less fancy and may not even seem like a technique at all. All going bottom up means is to ditch recursion and use some other approach like a loop to solve the same problem. The reason that going bottom up is considered part of dynamic programming is because dynamic programming means taking a problem that could be solved recursively and ensure that it doesn't make duplicate calls for overlapping sub-problems. So dynamic programming simply means that we're using a way or means taking a problem that could be solved recursively and ensure that it doesn't make duplicate calls for overlapping sub-problems. So therefore, we can also use loop aside from this you call this memorization or memorization. Using iteration, that is loops, instead of recursion is technically a way to achieve this. Going bottom up becomes more of a technique when the problem is more naturally solved with recursion. Generating Fibonacci number is one example where recursion is a neat, elegant solution. Having to solve the same problem with iteration may take more brain power, as an iterative approach may be less intuitive. So again, it's like in the interaction design video, the more natural and intuitive the problem approach is, therefore that's the right interface or the right tool to solve the problem. Kinda like in the about face video, in which anyone would agree that if you use a wrong tool, it will eventually catch up on you. So it's still the same here. For some problem, it takes more brain power for you to use loops than recursion. But for some problem, it takes more brain power to use recursive than to use loops. So the key is knowing what tools to use in problems you are trying to solve. So kind of like the app that I've created. So I created a video call and share screen application for doctors, and I used LiveKit for creating that. So I did that for less than a week because I choose the right tool. So I make sure that we have the right options, or I mean I check all the available options using research, and then I use the right tool, because had I used a wrong tool, it would be impossible for me to create that in a week. Yeah, so that's the importance again of using the right tool. So again, I think I don't need to repeat that key principle here. So let's continue. Going bottom up becomes more of a technique when the problem is more naturally solved with recursion. Generating Fibonacci numbers is one example where recursion is a neat, elegant solution. Having to solve the same problem with iteration may take more brain power, as an iterative approach may be less intuitive. Imagine solving staircase problem from the previous chapter with a loop. Ugh. So staircase problem, in that case, you need to use recursion, because by going top to bottom, you're able to solve all the bottom problem for all cases without having to go into the details. So staircase problem is kind of like better fit for recursive function. So if you use a loop, it will take you a lot of brain power to solve that. So let's see how we might implement a bottom-up approach for a Fibonacci function. In the following bottom-up approach, we start with the first two Fibonacci numbers, 0 and 1. We then use good all iteration to build up the sequence. So here, def fib parameter n again. If n equals to 0, return 0. A and B start with the first two numbers in the series respectively. Sorry about that. So A equals initially 0, B is equals to 1. Loop from 1 until n for I in range 1, comma n. A and B each move up to the next numbers in the series. Namely, B becomes the sum of B plus A, and A becomes what B used to be. So again, for I, so we initiate A equals to 0 and B equals to 1 as a base case, and when we use loop from 1 until n, for I in range 1, comma n, and then column, A and B each move up to the next number in the series, namely, B becomes the sum of B plus A. So B becomes the sum of B plus A, and A becomes what B used to be, because we iterate on all the subsequent numbers. We utilize a temporary variable to make these changes. So temp equals to A, then A is equals to B, because it becomes B, and then B equals to temp plus A, and B becomes the sum of B plus A, and then we return the B. So here we start variables A and B as 0 and 1 respectively, so that's just the initial value, as those are the first two numbers of the Fibonacci sequence. We then again, so we start at the end here, since we know that those are the first numbers every time, so those are one of the characteristics of Fibonacci. We then start a loop so we can calculate each number of the sequence until we reach n. Then we start a loop so we can calculate each number of the sequence until we reach n. So since we know that 0, 1 is the base case, we start a loop so we can calculate each number of the sequence until we reach n, or the Fibonacci value we want to know. So for I in range 1, n, so to calculate the next number in the sequence, we need to add the two previous numbers. So we assign temp to the second most recent value and to the most recent value. So we assign temp to the second most recent value and A to the most recent value. So second most recent is assigned to temp, and the most recent is assigned to A. So the new number in the sequence, which will reassign to B, is the sum of those previous numbers. So since we're adding those previous numbers, here B is equal to temp plus A. Remember the Fibonacci is 1, 0, 1, and then 1, and then 2, and then 3, and then 5, because we're adding the previous one. So here's the code. Because our code is a simple loop from 1 to n, our code takes n steps, like the memorization approach or memoization approach. It's ON. Now, memoization versus bottom up, usually it depends on the problem and why you're using recursion in the first place. If recursion represents an elegant and intuitive solution to a given problem, you may want to stick with it and use memoization to deal with any overlapping subproblems. So we can use loop or memoization to solve overlapping subproblems. However, if the iterative approach is equally intuitive, you may want to go with that. And additionally, for general cases, you may want to use the iterative or loop approach, and then use memoization at considerable, not maybe like some for some time if it's really applicable. It's important to point out that even with memoization, recursion does carry some extra overhead versus iteration, and because of this, recursion always have extra overhead versus iteration. Specifically with any recursion, the computer needs to keep track of all the calls in a call stack. So because memorization or memoization needs to remember that in a call stack. Remember, recursive stem from a stack, so it needs to specifically for this, it needs to remember that in a stack. In this case, the data structure is actually a hash table, which consumes memory. The memoization itself also requires the use of a hash table, which will take up additional space on your computer as well. So it's not just talk, but it also use a hash table. Kind of like when you open an application and you undo a lot. So the computer or the application needs to save a lot and consume that memory that could be available from other application. So that could crash your application if you're not careful, because yeah, it will cause, sometimes it will cause bug as especially if people use your app. It's a sovereign application where people use your app all the time. Now, the memorization itself also requires the use of hash table, which will take up additional space on your computer as well. More on this in dealing with space constraints. Generally speaking, going bottom up is often better choice unless the recursive solution is more intuitive. Where recursion is more intuitive, you can keep the recursion and keep it fast by using memorization. So again, generally speaking, going bottom up is often better choice unless the recursive solution is more intuitive. So for recursive, we usually do that using a top to bottom, but for bottom up, we usually use loops. So that is generally better, like what I've said, because the recursive consume a lot of memory. Where recursion is more intuitive, you can keep the recursion and keep it fast by using memorization or memoization, or at least use the overlapping subproblems or storing it in a variable if that's applicable. In the next section, we'll encounter some really efficient yet advanced algorithm, and many of them rely on the principle of recursion. So recursing algorithm for speeds. So in previous chapters, we've encountered a number of sorting algorithms, including bubble sort, selection sort, and insertion sort. In real life, however, none of these methods actually use to sort arrays. Most computer languages have built-in sorting functions for arrays that save us the time and effort of implementing our own. So most programming languages, when we use array to create our program, it actually use quick sort to sort the data. So and because it's more efficient in average cases. So as we know, in the bell curve, average cases is what happens most of the time. And in many of these languages, the sorting algorithm that is employed under the hood is quicksort. The reason we're going to dig into quicksort, even though it's already built into many computer language, is because by studying how it works, you can learn how to use recursion to greatly speed up algorithm. So we mentioned that we rarely use recursion for iterating or like because it consumes a lot of memory, but it's different for sorting algorithms because it actually uses recursive algorithm or recursion underneath, but it's all abstracted to us using our programming language. So it's essential to understand that, because that's how we actually sort, which is one of the most useful algorithms we use today. So that's actually how we sort it using recursion. So you can learn how to use recursion to greatly speed up an algorithm, and you can do the same for other practical algorithms of the real world. Quicksort is an extremely fast sorting algorithm that is particularly efficient for average scenarios. While in worst case scenarios, that is inversely sorted arrays, it performs similarly to insertion sort and selection sort. So in a worst case scenario, that is inversely sorted arrays, so in which you need to sort it individually, therefore you need to search it, right, the value first for everything, and then compare and shift it away. It takes n squared as well. It performs similarly to insertion sort and selection sort. Remember, insertion sort are good for best case scenario, and selection sort are best for worst case scenario because it's n squared over 2. It's much faster for here. quicksort is faster for average scenario, which are what occurs most of the time. So to understand quicksort, we need to understand partitioning. So to partition an array is to take a random value from an array, which is then called the pivot, and make sure that every number that is less than the pivot ends to the left of the pivot, and that every number greater than the pivot ends up to the right of the pivot. We accomplish partitioning through a simple algorithm that will be described in the following example. So again, a pivot, make sure that every number that is less than the pivot ends up to the left of the pivot, and that every number greater than the pivot ends up to the right of the pivot. Kind of like you're sorting it, but you're using a less than or greater than. So here, we're gonna see an example. So this concept are important for us to understand how quicksort works. Let's see. Let's just make it larger. So first, let's say we have the following array 0, 5, 2, 1, 6, 3. For consistency's sake, we'll always select the rightmost value to be our pivot, although we can technically choose other values like in the middle or in the beginning. In this case, the number 3 is our pivot. I mean, we're putting that on the right because we need to compare if the left side should be less than, and then if the right side should be greater than. We can technically choose 5 as our pivot, but for consistency's sake, we're gonna choose 3. So we indicate this by circling it. We then assign pointers, one to the leftmost value of the array and one to the rightmost value of the array, excluding the pivot itself. So we exclude the pivot and then we assign pointers. So we're gonna do that using our code later. So on the left of the leftmost, which is the first index, and the rightmost, which is in this case the last index. So we're now ready to begin the actual partition, which follow these steps. Don't worry, the steps will become clearer when we walk through our example shortly. The left pointer continuously moves one cell to the right until it reaches a value that is greater than or equal to the pivot and then stops. So the left pointer continuously moves one cell to the right until it reaches a value that is greater than or equal to the pivot, greater than here. It will stop this once we reach 5 because it's greater than 3. Then the right pointer continuously moves one cell to the left until it reaches the value that is less than or equal to the pivot. So if it's it will stop here on 1 because that's where the value is less than or equal to 3. And then stops. The right pointer will also stop if it reaches the beginning of the array. Another characteristic of the right pointer is that it will stop if it reaches the beginning of the array. So notice how it's different from the left pointer, where the left pointer will not stop until the end of the array because that's where the pivot is residing. So we're only stopping from the beginning of the array when we're coming from right pointer. Once the right pointer has stopped, we reach a crossroads. If the left pointer has reached or gone beyond the right pointer, so once the right pointer has stopped, we reach a crossroads. So once the left, right stop and then right pointer stop, we reach a crossroad. Notice we start from the left and then right pointer. And then if both start, it means that we reach once the right pointer has stopped, we reach a crossroad. So since that is the second from the left, it means that the left pointer has stopped already when the right pointer has stopped. If the left pointer has reached or gone beyond the right pointer, we move on to step 4. So we're gonna use if else statement there. If the left pointer go beyond where the right pointer is. Otherwise, we swap the values that the left and right pointers are pointing to, and then go back to repeat step 1, 2, and 3 again. Finally, so if the left goes beyond the right pointer, we swap the pivot with the value that the left pointer is currently pointing to. So if that's the case, the left pointer reach or move past the right, we swap that with the pivot. So when we're done with the partition, we are now assured that all values to the left of the pivot are less than the pivot, and all values to the right of the pivot are greater than it. And that means the pivot itself is now in its correct place within the array, although the other values are not yet necessarily completely sorted. So so other values may not be completely sorted once we get into this rightmost and leftmost sorted pivot. Now step 1, let's apply this to our example. Compare the left pointer now pointing to 0 to our pivot, the value 3. Since 0 is less than the pivot, the left pointer moves on to the next step. Then next step, the left pointer moves on. We compare. So let's notice we compare what this the step here or operations we did. Another in step 2, we compare again the left pointer, the 5, to our pivot. Is the 5 lower than the pivot? It's not. So the left pointer stops and we activate the right pointer in our next step. So again, we stop the left pointer and we move on to the right. And then compare the right pointer. So that's another operation or step. Steps 3. Compare the right pointer 6 to our pivot. Is the value greater than the pivot? It is. So our pointer will move on in the next step. Step 4. The right pointer moves on. We compare the right pointer 1 to our pivot. Is the value of our pivot greater than is the value 1 greater than the pivot? It's not. So our right pointer stops. Since both pointers have stopped, we swap the values of the 2 pointers. So since that right value stopped, we swap the value of the 2 pointers. Since this case, the left pointer did not move past the right, and both left and right move from their respective without moving past both of them. Therefore, we need to swap where the left and right pointer stops. So that's the step 4. Since step that's the step 5. Since both pointers have 5, we swap the values of the pointers. So that's another operations we did. We swap. We then activate our left pointers again in the next step. So step 6. So again, step 5 is swap, and then step 4 still compare. Step 6, the left pointer moves on, and then it's compare again. We compare the left pointer 2 to our pivot. Is the value less than the pivot? It is. So the left pointer moves on. So that's step 6. Step 7, the left pointer moves on to the next. Note at this point, both the left and the right pointers are pointing to the same value. So we compared the left pointer to our pivot 3. Because our left pointer is pointing to a value that is greater than our pivot, it stops. At this point, since our left pointer has reached, so again, we compare, it's comparison step again. At this point, since our left pointer has reached our right pointer, we're done with the with moving pointers. For a final step of the partition, we swap the value that the left pointer is pointing to with the pivot. So here, since both point in the same arrow, it will stop, right? Because when we move to the right pointer, it will compare the next cell, which in this case, the left cell will move past that. Therefore, we need to exchange the pivot value and the left cell pointer, which is the step 4 of our code. So we swap the 3 and 5. So for our final step, we swap the value. So that is a swap operation. Although our array isn't completely sorted, we have successfully completed the partition. We know that the left pivot are less than, and then right pivot are than it. So although our array isn't completely sorted, we have successfully completed a partition. That is, since our pivot was the number 3, all numbers that are less than 3 are to its left, while all numbers greater than 3 are to its right. This also means, by definition, that 3 is now in its correct place within the array. Code implementation of partitioning. Following is an implementation of a sortable array, a class in Ruby that includes partition method that partition the array as we've described. So we created class sortable array. We created attr underscore reader array, and then we define initialize method from that class, which has a parameter array, and then at array equals to array, and then end. And then after that, we define partition, and then parameter left underscore pointer, and then right pointer. So we always choose the rightmost element as the pivot. We keep the index of the pivot for later use. So we always choose the rightmost element as the pivot. So pivot underscore index equals to right underscore pointer. We grab the pivot value itself. Pivot equals to at array pivot underscore index. So that's how we grab that pivot. We start the right pointer immediately to the left of the pivot. Right pointer is negative equals to 1. So that's actually how we decrement the index or decrement the pointer. Now we initiate a while loop in this class after that partition method. Inside that partition method, move the left pointer to the right as long as it points to value that is less than the pivot. While true, so we use while true. After that, there's a nested while again. While at array left underscore pointer less than pivot, do left pointer plus equals to 1, and then end. So another while loop in this while true parent loop. So what this does on that first child while loop is that it moves the left pointer to the right as long as it points to value that is less than the pivot. So it moves to the right as long as it's less than the pivot. If it's greater than, it's stop, or greater than equal. So here another while loop, child while loop of this parent while loop in this class. While at array right underscore pointer is greater than pivot, do right pointer negative minus equal 1, and then end. So here what this while loop or child while loop does is it moves the right pointer to the left as long as it points to a value that is greater than the pivot. We've now reached the point where we've stopped moving both the left and right pointers. So this is the step 1 and 2 in the earlier pseudocode we wrote. So we check whether the left pointer has reached or gone beyond the right pointer. So here we use an if-else statement for this, another child if-else statement of that while loop. If left pointer is greater than equal right pointer, we break it. So here we check whether the left pointer has reached or gone beyond the right pointer. So this is the step 3. If it has, we break out the loop so we can swap the pivot later on in our code. So we break that if it is. Now this is where the stepper is. If the left, so else, after that break statement we have a else child loop of that while true loop. Else array left underscore pointer comma array right underscore pointer equals to array right underscore pointer comma array left underscore pointer. So after we break that, we swap the left and then the right pointer. So if the left pointer is still to the left of the right pointer, we swap the values of the left and right pointer, so that this else does. So we move the left pointer over to the right, gearing up for the next round of while true loop of left and right pointer movement. So left underscore pointer plus equals 1, and then end this while true, and then end the entire class. So here, as the final step of the partition, we swap the value of the left pointer with the pivot. So this is how since we break that earlier in a if statement, here's how we're gonna swap that. As the final step of the partition, we swap the value of the left pointer with the pivot. At array left underscore pointer, comma, array at array pivot underscore index equals to at array pivot underscore index, comma, array left underscore pointer. So at array left underscore pointer, comma, at array pivot underscore index equals to at array pivot underscore index, comma, at array left underscore pointer. So we swap that value. We return the left pointer for the sake of the quicksort method, which will appear later in this chapter. Return left pointer, then end, and then end. So if we break, we move past this code, and then we end, and then we end again. So the partition method accepts the starting points of the left and right pointers parameters. So it accepts this left and right pointer as a parameter where you want to start in that index of the array. When this method is first called on an array, these points will point to the left and right ends of the array respectively. So when we put this left underscore pointer and right pointer, this will be the first and the last index, second to the last index of the array respectively. However, we'll see that quicksort will call this method on subsections of the array as well. Because of this, we can always assume the left and right pointers are always the two extremities of the array, so they need to become method arguments. This point will be clearer when I complete the quicksort algorithm. So again, let's repeat this. When this method is first called on an array, these pointers will point to the left and right ends of the array. So first called, it will in the first index and last index respectively. However, we'll see that quicksort will call this method on subsections of the array as well. So quicksort will actually call this as a sub array, kind of like a binary search where it divides this the left or right array depending on where most likely the value we're finding or the pivot is. So because of this, we can always assume the left and right pointers are always the two extremities of the array, because when we have that, it could be the extreme rightmost is at the middlemost because we divide that by 2. So they need to become method arguments. This point will be clearer when I explain the quicksort algorithm. Next, we select our pivot, which is always the rightmost element in the range we're dealing with. So pivot underscore index equals to right underscore pointer, and then pivot is equals to at array pivot underscore index. So we'll select our pivot, which is always the rightmost element in the array in this case. So once our pivot has been identified, let's see, we move to the right pointer to the item immediately left of the pivot. We begin a loop that will run until the left pointer and right pointer meet. So while at array left underscore pointer less than pivot, do left underscore pointer plus equals to 1. This is inside the while true loop. So that's the first child while loop. Once the left, so again, we then begin a loop that will run until the left underscore pointer and right underscore pointer meet. So while at array left underscore pointer less than pivot, do left underscore pointer plus equals 1. So this is the first criteria of our pseudocode. We then begin a loop that will run this. Within this loop, we use another loop to keep moving left underscore pointer to the right until it reaches an item that is greater or equal to the pivot. So that is left underscore pointer plus equals to 1 until it reach a value in which it's less than or equal, greater or equal the pivot. So once the left underscore pointer and right underscore pointer have stopped moving, so here if left underscore pointer greater than or equals to right pointer stop moving, we check whether the two pointers have met. So we break that again. So as I've explained, if they have, we exit the loop and get ready to swap the pivot, which will get 2 momentarily. However, if the two pointers have not yet met, we swap the values at the 2 pointers. So if it didn't break here, we swap the 2 pointers. If the 2 pointers have not yet met, we swap the values of the 2 pointers. So this is the step 3. Array left on the pseudocode underscore pointer, array right. So we swap those 2 pointers. Finally, once the 2 pointers have met, we swap the pivot with the value at the left pointer. So again, we swap that at the left pointer like what we did in the pseudocode. Not in the right pointer, by the way. So the method returns the left underscore pointer, as this will be needed by the quicksort algorithm, which we'll explain shortly. So quicksort, the method returns left underscore pointer. This will be needed by the quicksort algorithm, right? So partition the array. So this is the step for quicksort. Partition the array. The pivot is now in its proper place. Treat the sub-arrays to the left and right of the pivot as their own arrays and recursively repeat steps 1 and 2. So this is where we use the recursive function in the left and right by treating the left and right of the array as its sub-array. That means after we partition, we'll partition each sub-array and end up with even smaller sub-arrays to the left and right of each sub-array's pivot. So once the pivot in its partition already in its proper place, we partition its left and right sub-arrays. Therefore, we find another pivot again, and then we recursively repeat steps 1 and 2. So 3 arrays we partition again. So this is, we use recursively by partitioning. So we use recurse function or recurse partition to call partition again within those left and right sub-array. That means we'll partition each sub-array and end up with even smaller sub-arrays to the left and right of each sub-array's pivot. We then partition those sub-arrays and so on and so forth. When we have a sub-array that has 0 or 1 elements, that is our base case, and we do nothing. So when we have a sub-array that has 0 or 1 elements, that is our base case, kind of like in our partition, and we do a recursive function. In that case, we do nothing. So let's return to our example. We began with the array of 0, 5, 2, 1, 6, 3, and run a single partition on the entire array. Since quicksort begins with such a partition, that means we're already partly through the quicksort process. So we left off with this. Now, you can think of quicksort as a combination of partition and recursive function, in which we use a recursive partition inside this partition function. If if it makes sense. So as you can see here, the first partition, it's almost already sorted already. So the 3. But we will start with this 3 on the left of it, and then right of it. We're gonna treat that as sub-arrays. As you can see, the value 3 was the original pivot. Now that the pivot is in the correct place, we need to sort whatever is to the left and right of the pivot. Note that in our example, it just so happens that the numbers to the left of the pivot are already sorted. But the computer doesn't know that yet, because we're gonna call the recurse inside our code. Therefore, we're going from top to bottom. So the computer will, we're asking the computer to do that recursive partition, even though that already is sorted, kind of like sorted, but the computer doesn't know that because we call that inside our code. So the next step after the partition is to treat everything to the left of the pivot as its own array and partition it. So we'll obscure the rest of the array for now. as we're not focusing on it at the moment. So here we have 0, 1, 2. Now of this 0, 1, 2 subarray, we'll make the rightmost element the pivot again. So that would be the number 2. Again, we're calling again the partition here. So we're calling the right as the most, or the pivot, the rightmost element as the pivot. And then we'll establish our left and right pointers. So and now we're ready to partition this subarray. Let's continue from after step 8 where we left off previously. Step 9, again we use comparison operation. We compare the left pointer 0 to the pivot 2. Since the 0 is less than the pivot, we continue moving the left pointer. Step 10, we move left pointer 1 cell to the right, and it now happens to be pointing the same value to the right pointer is pointing to. Again, we use comparison steps here. We compare the left pointer to the pivot. Since the value 1 is less than the pivot, we move on. So as you notice, we passed on the right pointer, which again, in this case, we need to move to the step 4 of our pseudocode. So step 11, we move to the left pointer 1 cell to the right, which just happened to be the pivot. At this point, the left pointer is pointing to a value that is equal to the pivot since it's pivot, and so the left pointer stop. So this left pointer stop. Now note how the left pointer managed to sneak past the right pointer. That's okay though, the algorithm is designed to work even with such occurrence. So as you can see, we move to the left and then we compare this to the pivot again. And then as you can see, the left pointer is pointing to the 2 and it's equal to the pivot. Now we activate the right pointer because that's the second of our pseudocode. Now we activate the right pointer, however, because the right pointer's value 1 is less than the pivot, it stays still. Since that's how our code is designed to do. So it's comparison step again. Since our left pointer has passed our right pointer, we're done moving pointers altogether in this partition. Next, we stop the pivot with the left pointer's value. So again, that's where we do the step 4 of our pseudocode now. Again, we start with the left pointer and right pointer, now the 4th step of the pseudocode. Now, next we swap the pivot with the left pointer's value. Now, it just so happens that the left pointer is pointing to the pivot itself. So we swap the pivot with itself, which results in no change at all. At this point, the partition is complete and the pivot 2 is now in its correct spot. So here, it's still the same array. We now have a subarray of 0, 1 to the left of the pivot, the 2, and no subarray to its right because we're just having it to the left, right? So we're focusing on the left subarray. The next step is recursively partition the subarray to the pivot step, which again 0, 1. We don't have to deal with any subarray to the right of the pivot since no subarray exists. Because we'll focus on in the next step is the subarray 0, 1. We'll block out the rest of the array so it looks like this. So the partition, to partition the subarray 0, 1, we'll make the rightmost element the 1. The pivot where we will put the left and right pointers. Well, the left pointer will point to the 0, but the right pointer will also point to the 0 since we always start the right pointer at 1 cell to the left of the pivot. So it's this gives us this, both left and right pointing to the. So we're now ready to begin the partition. Step 14, we compare again. We compare the left pointer 0 with the right pivot 1. It's less than the pivot, so we move on. Again, we pass the left to the right. So what happened? We shift in the left pointer 1 cell to the right. It now points to the pivot. Since the so that's a step 15. Since the left pointer's value 1 is not lower than the pivot, since it's the pivot, the left pointer stops moving. So since it's equal to the pivot, it stops moving. Now we move on to the right pointer, which is step 2. So again, comparison step here. We shift the left pointer 1 cell to the right. It now points to the pivot. Yeah, so it's still a comparison operation. Now we compare again in step 16 the right pointer which is the second step of the pseudocode, with a pivot. Since it's pointing to a value that is less than the pivot, we don't move it anymore. And since the left pointer has passed the right pointer, we're done moving pointers for this partition. So again, we compare the right pointer with the pivot. Since in pointing to value that is less than the pivot or equal it, we don't move it anymore. And since the left pointer has passed the right pointer, we're done moving the pointers for this partition. Step 17. We now swap the left pointer with the pivot. Again, in this case, the left pointer actually pointing to the pivot itself. So the swap doesn't actually change anything. The pivot is now in the proper place and we're done with this partition. So as you can see, we've done two partition in this left subarray. That leaves us with this. It's still the same array. Now, next we need to partition the subarray to the left of the most recent pivot. So here, 6, 5. In this case, the subarray is 0, an array of just one element. So next up, we need to partition the subarray to the left of the most recent pivot. We actually have one array 0. In this case, the subarray is 0. An array is of just one element, which is our base case. An array of 0 or one element is our base case, so we don't need to do anything. The element is just considered to be in its proper place automatically. So now we've got 0, 1, 2, 3, 6, 5. So we started out by treating 3 as our pivot and recursively partition the subarray to its left 0, 1, 2. So the reason why we're able to partition this left subarray is because we started by 3 as our left pivot. So we started out by treating 3 as our pivot and recursively partition the subarray to its left 0, 1, 2 as promised. We now need to come back to recursively partitioning the subarray to the right of 3, which is 6, 5. Now we'll obscure 0, 1, 2, 3 since we've already sorted those and we're only focusing on the 6, 5. In the next partition, we'll treat the rightmost element, the 5, as the pivot. That gives us this. So when setting up our next partition, our left and right pointers both ends up pointing to the 6. And then step 18, we compare the left pointer 6 with the pivot 5. Since 6 is greater than the pivot, the left pointer doesn't move further. So again, we have comparison with the left pointer. It's the first of our pseudocode with a pivot 5. Since 6 is greater than the pivot, then the left pointer stops and doesn't move further. So it's a comparison operation. Step 19, the right pointer is pointing to the 6 as well. So we would theoretically move on to the next cell to the left. So the right pointer is pointing to the 6 as well. So we would theoretically move on to the next cell to the left. However, there are no more cells to the left of the 6 because we divide that to the subarray of 3 to the right. So the right pointer stops moving. Since the left pointer has reached the right pointer, we're done moving pointers altogether for this partition. That means we're ready for the final step. So step 20, swap operation. We swap the pivot with the value of the left pointer. Our pivot 5 is now in its correct spot, leaving us with 6. Next up, we need to recursively partition the subarray to the left and right of the 5, 6 subarray. Since there's no subarray to its left, that means we only need to partition the subarray to the right. Since the subarray to the right of the 5 is a single element of the 6, that's our base case. And we do nothing. The 6 is automatically considered to be in the right place. So here's the code implementation of this long algorithm, but it's very useful because it's what we actually use or programming use, language use underneath of their sorting function. So following a quicksort method, we can add to the previous sortable array class that would successfully complete the quicksort. So def quicksort left underscore index right index base case. The subarray is a 0 or 1 element if right underscore index minus left underscore index is less than or equal 0, return, then end. And then here's the call for partition. So we're gonna call this recursively inside of our quicksort. Partition the range of elements and grab the index of the pivot. Pivot underscore index equals to partition exclamation left underscore index right underscore index. So it means we partition the range of elements and grab the index of the pivot. So after we partition that, we grab the index or pivot underscore index, partition left underscore index and right. So we partition the whole array first. So this is still inside the quicksort function. So quicksort exclamation left underscore index, comma, pivot underscore index minus 1. So it means recursively call this quicksort exclamation method on whatever is to the left of the pivot. So this is actually how we recursively partition the left of the pivot. So we use quicksort instead of partition. So left underscore index comma pivot index minus 1, because we're gonna use the pivot value as our rightmost or as a new pivot, and then we minus 1 as our end of the index we want to recursively partition. Now last function, recursively call this quicksort exclamation pivot underscore index plus 1, and then comma right underscore index. So this means recursively call this quicksort method on whatever is to the right of the pivot and then end. So the code here is surprisingly concise, but let's look at each line. So the key here is the partition. This is the long code. So we're gonna define this after the that partition code, of course. So this is where that partition came from our previous partition code. Now the code is surprisingly concise, but let's look at each line. For now, we'll skip over the base case. We begin by partitioning the range of elements between left underscore index and right underscore index. So here, pivot underscore index partition. So the first time we run quicksort, we partition the entire array. In subsequent calls, so the first time, this is how we partition the whole array. In subsequent call, though, this line of code partition whatever range of elements lies between left underscore index and right underscore index, which may be a subsection of the original array. Note that we assign the return value of partition exclamation to a variable called pivot underscore index, because we're gonna use that on left and right partition, because that will be the leftmost and rightmost of the partition. If you recall, this value was the left underscore pointer, which pointed to the pivot by the time the partition method was complete. We then recursively call quicksort on the subarray to the left and right of the pivot. So the recursion ends when we reach the base case, which is when the subarray at hand contains no more one element. So notice this, in this recursion or quicksort method, there's still taste of recursion, in which we use base case and recursion along with the binary search under the hood. So here is where it will all return to once it's 0 element. So we can take our quicksort implementation for a test drive using the following code: array 052163 sortable underscore array equals to sortable array dot new array. So we input that array, and then sortable underscore array dot quicksort exclamation start with 0, and then array dot length minus 1, and then p sortable underscore array. So as you can see, this sortable underscore array, these are the class we created for our partition earlier here, sortable array. So this is how we define the partition. So that's actually included in the quicksort. So you can see this sorting algorithm is very long and complex, but it's helpful to understand. So the efficiency of quicksort. The efficiency of quicksort, let's first determine the efficiency of a single partition. When we break down the steps of a partition, we'll note that a partition involves two primary types of steps: comparisons and swaps. We don't actually ship when we move. We compare that to the pivot, or on the on the pivot or in the right pointer, left or right pointer. Comparison, we compare each of the values at hand to the pivot. Swaps, When appropriate, we swap the values being pointed to by left and right pointers. So each partition has at least n comparisons. That is, we compare each element of the array with the pivot. So each partition has at least n comparisons. Again, as you notice, we have a lot of comparison because that is, we compare each element of the array with the pivot. So this is true because a partition always has the left and right pointers move through each cell until the left and right pointers reach each other. So the number of swaps, however, will depend upon how the data is stored. So the swap is not as huge as a comparison. A single partition can have at most n over 2 swaps. So in the worst case scenario, a single partition would have n over 2 swaps because again it will divide that into a left and rightmost values, as even if we swap values at every opportunity, each swap takes care of 2 values. So as you can see in the following diagram, we partition 6 elements in just 3 swaps. So 3 elements are partitioned in just 3 swaps. Now in most cases, we're not making a swap every step of the way. For a randomly sorted data, we generally swap about half of the values. So for a randomly sorted, we generally swap about half of the values. On average, then, we're making about n over 4 swaps in average case. So in worst case is n over 2. So in average case, we make about n comparisons and n over 4 swaps. So that's what, 1/4 n. We can say that they're about 1.25. 1.25 n steps for n data elements. In big O notation, we ignore constants, so we'd say that a partition runs in O n time. So this is where the quicksort are better in average scenario than selection and insertion sort. Now that's the efficiency of single partition, but quicksort involves partitions. So that's the efficiency of a single partition. But a quicksort involves many partitions, so we need to conduct further analysis to determine the efficiency of quicksort. So that's just an efficiency of 1.25 n step, or just efficiency of a single partition. But we need to calculate all the efficiency of each partition. Now quicksort from a bird's eye view. So here we're gonna calculate the other partitions that we made. So to visualize this more easily, here's a diagram depicting a typical quicksort on an array of 8 elements from a bird's eye view. In particular, the diagram shows how many elements each partition acts upon. We've left out the actual numbers from the array since the exact values don't matter. Note that in this diagram, the active sub-array is the group of cells that is not grayed out. We can see that we have 8 partitions, but each partition takes place on sub-array of various sizes. We perform a partition on the original array of 8 elements, but also perform partition on sub-arrays of 4, 3, and 2, and another 4 partition on arrays of size 1. Since quicksort is essentially comprised of this series of partition and each partition takes about n steps for n elements of each sub-array, if we add the sizes of all the sub-arrays together, we'll get the number of steps quicksort takes. So here, partition 1, 0 elements, partition 2, 3 elements, partition 3, 1 element, partition 4, 1 element, partition 5, 4 elements, partition 6, 2 elements, partition 7, 1 element, partition 8, 1 element. So 8 plus 3 plus 1 plus 1 plus 4 plus 2 plus 1 plus 1 element, total is equals to about 21 steps. We see, from the first partition, which started from 1.25 n steps plus all this other partition of the sub-array, we see that where the original array has 8 elements, quicksort takes about 21 steps. This assumes a best or average case scenario, where the pivot ends up roughly in the middle of the sub-array after each partition. So if the pivot roughly are located or placed in the middle of the array or in average or best case scenario, this is the efficiency. For an array of 16 element, quicksort takes about 60% steps. For an array of 32 elements, quicksort takes about 60 steps. Take a look at this table. So while in our example earlier, the number of quicksort steps for an array of size 8 was 21, I put 24 in this table. The exact number can vary from case to case, and 24 is also a reasonable approximation. I specifically made it 24 to make the following explanation a little bit clearer. So the big O of quicksort. So how do we categorize quicksort in terms of big O notation? So here it is. If you look at the pattern shown earlier, we'll note that the number of quicksort steps for n elements in the array is about n multiplied by log n, as shown in the following code. Notice this is a new category of big O that we're introducing. So here n for L elements, log n 2, and then n log n is 8. Quicksort steps is 8. For 8n and log n is equals to 3, n log n is 24 because 3 times 8. So now it's not a coincidence that the number of steps in quicksort just happens to align with n log n. If we think about quicksort more broadly, we can see why it is this way. Each time we partition the array, we'd end up breaking it down into two sub-arrays, which is the log n. Assuming the pivot ends up somewhere in the middle of the array, which is what happens in the average case, these two sub-arrays are of equal sizes. So that's why we have n log n. So it's the graph of the all of the categories that we have discussed so far. On log n, on. So on log n is much slower than on. So log n is the fastest. So on log n is much slower. So how many times can we break an array into halves until we're breaking it completely down to a point of where each sub-array is of size 1. For an array of size n, this will take us log n times. Take a look at the following diagram. So how many times can we break an array into halves until we've broken it completely down to the point where each sub-array is of size 1? For an array of size n, this will take us log n times until we break that divided by 2. Kind of like a binary search, right? That's the efficiency of binary search. So as you can see, an array of size 8, it takes us 3 halvings until we reduce the array into 8 individual elements. This is log n, and this is fits with our definition of log n as being the number of times it takes to have something until we reach 1. So this is why quicksort takes n log n steps. We have log n halvings, and for each halving, we perform a partition on all the sub-arrays whose elements add up to n. They add up to n because all the sub-arrays are simply pieces of the original array of n elements. This illustrated in the previous diagram at the top of the diagram. For example, we partitioned the original array of 8 elements, creating two sub-arrays of size 4. We then partition both sub-arrays of size 4, which means that we are again partitioning 8 elements. Bear in mind that on log n is just an approximation. In reality, we first perform an on partition in the original array, as well additionally an array doesn't clearly break into 2 even halves since the pivot is not part of the halving. So this is a more realistic example of what it really looks like. On log n is just an approximation. Now quicksort in the worst case scenario. For many other algorithms we've encountered, the best case was one where the array was already sorted. When it comes to quicksort, however, the best case scenario is one in which the pivot already ends up smack in the middle of the sub-array after the partition. For many other algorithms, again, the best case is where the array is already sorted. But when it comes to quicksort, the best case scenario is one in which the pivot always ends up smack in the middle of the sub-array. That's why it's better for average case scenario. The worst case scenario for quicksort is one in which the pivot always ends up on one side of the sub-array instead in the middle. So the worst case for the quicksort is one in which the pivot always ends up one side of the sub-array instead of in the middle. So that's actually the worst case in this pivot, or sorry, in this sorting, unlike other or sorting, unlike insertion and selection sort. So this can happen where the array is in perfect ascending or descending order, which is happens rarely. So there's a visualization of that. Partition 1, we have 8 elements. Partition 2, 7 elements. Partition 3, 6. And then 4, 5, 5, 4, 6, 3, 7, 2, 8, 1. So while in this case, each partition still involves only one swap rather, we lose out because of the increased number of comparisons. So while in this partition is only have one swap, we lose out because of the increased number of comparison. In the first example, when the pivot always end up toward the middle, each partition after the so let's unpack this. So basically, though we only have one swap here, we lose out because of the increase or exponential number, not exponential, increased number in comparisons. As you have learned, we're actually determining the efficiency based on the number of steps, and this comparison is considered the step of an algorithm. Now, in the first example, when the pivot always ended up toward the middle, each partition after the first one was conducted on a relatively small sub-arrays because it's in the middle, kind of like in binary search. So once you get into the middle, you ended up removing a lot of unnecessary steps. The largest sub-array had size of 4. In this example, however, the first 5 partition takes place on sub-arrays of size 4 or greater, and each of these partition have as many comparisons as there are elements in the sub-array. So in this, the worst case scenario, we have partition of 8 plus 7 plus 5 plus 4 plus 3 plus 2 plus 1 elements, which yields a total of 36 comparison compared to average of 21. To put this a little more formulaically, would say that for n elements, there are n plus n minus 1 plus n minus 2 plus n minus 3, etc. Step we saw in our discussion of get all the products that this computes to n squared over 2 steps, which is for the purposes of big O is n squared. It's like the selection sort in worst case scenario. Now quick sort versus insertion sort, because quick sort superiority in average circumstances, many programming languages use quick sort under the hood of their built-in sorting function. Because of this, it's unlikely you'll be implementing quick sort yourself. However, there is very similar algorithm that came in handy for practical cases, and it's called quick select. So here, for best case, insertion sort is ON, which is faster than quick sort, which is ON log n. Now for average case, insertion sort is n squared, which for quick sort is ON log n. For worst case, they're the same, it's the same n squared. So as you know, you can see the worst case or the best that sorting could do or is an ON log n. So you can use that for your future algorithms for sorting, because this will stem all the future algorithm that we will gonna discuss. So let's say you have an array in random order. So this is for quick select. This is a better and improved version of quick sort. Now let's say you have an array in random order, and you do not need to sort it, but you do want the 10th lowest value in the array or the 5th highest. So quick sort, if quick sort is combination of partition and a binary search, here quick select is kind of like more efficient use of quick sort. So since we just want to know the 10th lowest value in the array or the 5th highest, this can be useful if we had a lot of test grids and want to know the 25th percentile was, or if you want to find the median grade. One way to solve this would be to sort the entire array and jump to the appropriate index. However, even were we to use a fast sorting algorithm like quicksort, This algorithm would take at least on log n for average cases. And while that isn't bad, we can do even better with a brilliant little algorithm known as quick select. Like quicksort, quick select relies on partitioning and can be thought of as a hybrid of quicksort and binary search. So actually, since quicksort is already kind of like a hybrid of partitioning and binary search, it's not actually a combination of binary search and a partition, because a binary search really divide things array by 2 and then remove the other half. For quicksort, you still have both halves or the array. You're just removing some unnecessary steps for average case. But here, we're entirely removing the left or the half of the array each time. Combination which make it you know make the speed from n log n to a better speed. So as you've learned in this chapter, after a partition, the pivot value ends up in the appropriate spot in the array. Quick select takes advantage of this in the following way. So let's say we have an array of 8 values and we want to find the second to lowest value within the array. So here, first we partition the entire array. After the partition, the pivot will hopefully end up somewhere toward the middle of the array. So here, the pivot is now in the correct spot, and since it's in the fifth cell, we know which value is the fifth lowest value within the array. So after the partition, we know that that is where the fifth value, because what a partition does is it places that into the correct percentile or correct cell location in the array. We know which value is the fifth lowest value within the array. Now we're looking for the second value, not the fifth lowest value. But we do know that the second lowest value is somewhere to the left of the pivot. We can now ignore everything to the right instead of still considering it, just like in the quick sort, and focus on the left side array. It's in this respect that quick select is similar to binary search. We keep dividing the array in half and focus on the half in which we know the value we're seeking for will be found. Next, we partition the sub-array to the left of the pivot. Let's say the new pivot of this array ends up in the third cell. Because again, a partition always makes it the pivot smack in the middle. We know that the value in the third cell is in the correct spot, meaning it's the third lowest value in the array. By definition, then, the second lowest value will be somewhere to its left. We can now partition the sub-array to the left of the third cell. After this next partition, the lowest and second lowest values will end up in their correct spots within the array. So here, you have a second lowest value. We can then grab the value from the second cell and know with confidence that it's the second lowest value in the entire array. One of the beautiful things about quick select is that we can find the correct value without having to sort the entire array. So we make the quick sort average case faster. Now with quick sort, each time we have the array, we needed to repartition every single element again in their sub-array form, because we need to sort everything, giving us on log n. With quick select, on the other hand, each time we cut the array in half, we only had to partition the half we cared, the half in which we know our value is to be found. So the efficiency of quick select, in our example of an array of 8 elements, we executed 3 partitions, one on an array of 8 elements and one on an array of 4 elements and one on a sub-array of 2 elements. Recall that each partition takes about n steps. For the sub-arrays, it's run upon. The total steps then for the 3 partition is 8 plus 4 plus 2 equals to 14 steps. So an array of 8 elements yields 14 steps. For an array of 64 elements, we run about 64 plus 32 plus 16 plus 8 plus 4 plus 2 equals 126. For 128, we would need about 254. And for 256, we end up with 510. we can see that we need about 2n steps. So we reduce the average case from n log n to 2n for n elements in the array. Another way to formulate this is to say that for n elements, we would need n plus n over 2 plus n over 4 plus n over 8 plus the 2 steps. This always turn out to be roughly 2n steps. Code implementation of quick select. So following is a quick select method that can be dropped into the sortable array class earlier. You'll note it's very similar with the quick sort method. Also, notice that this quick select and the quick sort method are dropped in that sortable array class, in which we can just get from our code or programming language using its function name, such as quick select or quick sort. So here, following our implementation of quick select method that can be dropped into a sortable array class earlier, you'll note that it's very similar to the quick sort method. So here, def quick select kth underscore lowest value, comma left underscore index, comma right underscore index. So in this case, we have 3 parameters. So here, if right, so we have first if else statement that ends quickly. If right underscore index minus left underscore index less than or equals to 0, return at array left underscore index. So it means if we reach a base case that is that the sub-array has 1 cell, we know we've found the value we're looking for. So that's what this code means. And then after that, we define a pivot underscore index equals to partition exclamation left underscore index right underscore index. It's the same with the quick sort. It means partition the array and grab the index of the pivot. So grab the middle. If what we're looking for is to the left of the pivot, if kth underscore lowest underscore value is less than pivot underscore index, recursively perform quick select on the sub-array to the left of the index. So we're gonna use recursion to the left of the index alone without doing it to the right. So that the code for that. So again, this is if else code. If else, and then else code, and then return, and then end. So this is the code for this. But here, as you can see, if kth underscore lowest underscore value less than the pivot underscore index, we recursively perform quick select. And the code for quick select recursive function is quick select exclamation kth underscore lowest underscore value, comma left underscore index, comma pivot underscore index minus 1, because we're recursively dividing that or finding the lowest value to the left only without the right. If what we're looking for is to the right of the pivot, as if kth underscore lowest underscore value is greater than pivot underscore index, recursively perform quick select on the sub-array to the right of the pivot. So if it's greater than pivot underscore index, we will use a quick select exclamation kth underscore lowest value, comma pivot underscore index plus 1, comma right index. Else, if kth dot lowest value equals to pivot index, if after the partition the pivot position is in the same spot as the kth lowest value, we found the value we're looking for. Therefore, return at array pivot underscore index and then end. So if you want second to the lowest value of an unsorted array, you'd run the following code. Let's say your array equals to 0, 50, 20, 10, 60, 30. Sortable underscore array equals to sortable array dot new array. So we're gonna create that new array that we have defined, and then p space sortable underscore array dot quick select exclamation with a parameter 1 comma 0 comma array dot length minus 1. So the first argument of the quick select method accepts the position you're looking for, starting at index 0. We put in 1 to represent the second to the lowest value. The second and third values are the left and right indexes of the array respectively. So again, the first argument of the quick select method accept the position you're looking for. So it accepts the position starting at index 0. We put in a 1 to represent the second to the lowest value we're trying to find. So the second and third values are the left and right indexes of the array respectively. So sorting as a key to other algorithms. Let's just check this. Yeah. So sorting as a key to other algorithms. So as of this writing, the fastest sorting algorithm with known have speeds O n log n. While quicksort is one of the most popular among them, there are many others as well. Merge sort is another well-known O n log n sorting algorithm, and I recommend you look it up as it's a beautiful recursive algorithm. So it's a recursive algorithm as well, kind of like the same as quicksort. The fact that the fastest sorting algorithm O n log n is quite important, as this implication for other algorithms as well. This is because there are algorithms that use sorting as a component of a larger process. For example, if you'll recall from speeding up your code with big O, we dealt with the problem of checking whether there are duplicate values within an array. The first solution we looked involved nested loops and have an efficiency of n squared. While we found a solution that took O(n), I parenthetically hinted at the disadvantage with that approach having to do with extra memory consumption. I'll eventually discuss this at length with dealing with space constraint. So let's assume that O(n) approach is out. Are there any other ways we can improve upon the quadratic n squared solution? Hint, the solution has something to do with sorting. We can actually build a beautiful algorithm if we pre-sort the array. So instead of finding the duplicate values using n squared, or instead of finding it using just an O(n), which consume a lot of memory, we can actually use the sorting algorithm to find the duplicate values by pre-sorting the array. Let's say the original array was 5, 9, 3, 2, 4, 5, 6. There are two instances of 5, so we do have a case of duplicates. Now, if we first sorted this array, it would become 2, 3, 4, 5, 5, 6, 9. Next, we can use a single loop to iterate over each number. As we inspect each number, we check whether it's identical to the next number. If it is, we'd found a duplicate. If we get to the end of the loop without finding a duplicate, then we know we have no duplicates. The trick here is that by pre-sorting the numbers, we'd end up bunching duplicate numbers together. In our example, we start by looking at our first number, which is 2. We check whether it's identical to the next number. The next number is 3, so they're not duplicates. We then check the 3 against the following number, which happens to be a 4, allowing us to move on. We check the 4 against the 5, and we move on again. At this point, we inspect the first 5 and check it against the following number, which is the second 5. Aha! We found a pair of duplicate numbers, and we can return true. Here's a JavaScript implementation of this. Function has duplicate parameter array, and then pre-sort here array.sort a comma b is to a less than b question -1 colon 1 colon. But it basically means pre-sort the array. In JavaScript, the valuing usage of the sort function is required to ensure that the numbers are in numerical order instead of alphabetical order. Now, for let I equals to 0, I is less than array.length minus 1, I plus plus increment. This code means iterate through the values in the array up until the last one. Now, if array I is equals to I plus 1, return true. That means if the value is identical to the next value in the array, we found a duplicate. So if that index and then index plus 1 is the same, therefore we found a duplicate. And then we return true, and then we close the loop. If we get to the end of the array without having returned true, it means there are no duplicates. We return false, and then close the function. Now, we start out by sorting the array. We can assume that JavaScript sort function has an efficiency of O(n) log n. Next, we spend up to n steps iterating through the array. Our algorithm then takes n log n plus n steps. So that's it. We've used sorting to develop an algorithm that is O(n) log n only, which is a significant improvement over the original n squared algorithm. So we use the JavaScript array.sort, which is a quick sort in the background, right? Uh, to have n log n in average cases, and then plus n steps. Next, we spent up to n step iterating through the array only. So our algorithm then reduced from n squared to on log n plus n step, which then reduced to n log n category. So plenty of algorithms employ sorting as part of a larger process. We know that anytime we do so, we have an algorithm that is at least on log n. Of course, the algorithm may be slower than this if it has other things going on, but we know that n log n will always be the baseline. The quicksort and quickselect algorithm are recursive algorithms that present beautiful and efficient solution to thorny problems. They're great examples of how a non-obvious but well thought out algorithms can boost performance. Now that we've seen some more advanced algorithms, we're now going to head in a new direction and explore a trove of additional data structures. Some of these data structures have operations that involve recursion, so we'll be fully prepared to tackle this now. Node-based data structure. For the next several chapters, we're going to explore a variety of data structure that all build upon a single concept, the node. As you'll see shortly, nodes are pieces of data that may be dispersed throughout the computer's memory. Node-based data structure offer new ways to organize and access data that provide a number of major performance advantage. So as you have recalled, an array needs a contiguous memory like this. But for node, it can be separated like this. And the great thing is that it's easy to implement, and then we can implement that in any programming language, though it's not built in to the programming language, just like an array. So we'll start with the linked list. Like an array, a linked list is a data structure that represent a list of items. So while on the surface, arrays and linked lists look and act quite similarly, there are big differences under the hood. As mentioned in why data structures matter, memory inside the computer can be visualized as a giant set of cells in which bits of data are stored. You learn that when creating an array, your code finds a contiguous group of empty cells in memory and designates them to store data for your application as shown. So this is like a better way of communicating on how the instructions you put on your code when creating an array find memory or allocate a contiguous memory. Your code actually finds a contiguous group of empty cells in memory and designates them to store data for your application as shown. So here's the graph for that. You also saw that computer has the ability to access any memory address in one step and can use that power to also immediately access any index within the array. So you also saw that the computer has the ability to access any memory address in one step and can use that power to also immediately access any index within the array. If you wrote code that said, look up the value at index 4, your computer could locate the cell in a single step. Again, this is because your program knows which memory address the array starts at, say memory address 1000, because you did actually allocate that using array.length, and your code will find a memory from that, and your computer automatically knows the address of 1000, and therefore knows that if it wants to look up at index 4, it should simply jump to memory address 1004. Linked lists, on the other hand, work quite differently. Instead of being a contiguous block of memory, the data from linked lists can be scattered across different cells throughout the computer's memory. Connected data that is dispersed throughout memory are known as nodes. In a linked list, each node represents one item in the list. The big question then is, if the nodes are not next to each other in memory, how does the computer know which nodes are part of the same linked list? So this is the key to the linked list. Each node also comes with a little extra information. Essentially, you're allocating two cells, namely the memory address of the next node in the list. So unlike an array which only allocates one cells in each value, node actually allocate two cells in memory. So this extra piece of data This pointer to the next node memory address is known as a link. Here is a visualized depiction of a linked list. So data, and then this is the link. So first, in the first cell you have data, in the second cell you have link. So that link has the memory address of the next list item. Now in this example, we have linked list that contains 4 pieces of data A, B, C, D. However, it uses 8 cells of memory to store this data because each node consists of 2 memory cells. So again, another characteristics of nodes is it has 2 memory cells. The first cell holds the actual data, while the second cell serves as a link that indicates where in memory the next node begins. The final node's link contains null since the linked list ends there. A linked list first node can also be referred to as its head and its final node as its tail. So I think there's some similarity of it from heap or stack or queue. I just don't remember. If the computer knows at which memory address the linked list begins, it has all it needs to begin working with the list. Since each node contains a link to the next node, all the computer needs to do is follow each link string together the entire list. The fact that a linked list data can be spread throughout the computer's memory is a potential advantage it has over the array. An array, by contrast, needs to find an entire block of contiguous cells to store its data, which can get increasingly difficult as the array size grows. Now, these details are managed by your programming language under the hood, so you may not have to worry about them. However, you'll see shortly that there are more tangible differences between linked lists and arrays that we can sink our teeth into. Implementing linked list. So again, if the computer knows at which memory address linked list begins, it has all it needs to begin working with the list. Since each node contains a link to the next node, all computer needs is to follow each thing to string together the entire list. So it has all the computer needs to work on that list of items. Now, the fact that a linked list data can be spread throughout the computer's memory is a potential advantage since it's a different data structure from an array. An array, by contrast, needs to find the entire block of contiguous cells to store its data, which can get increasingly difficult as the array size grows. Now, these details are managed by your programming language under the hood, so you may not have to worry about them. However, you'll see shortly that there are more tangible differences between linked list and arrays that we can sink our teeth into. So implementing linked list. Some programming languages such as Java come with linked list built into the language. However, many languages do not, and it's fairly simple to implement them on our own. Let's create our own linked list using Ruby. We'll use 2 classes to implement this, node and linked list class. Let's create node class first. So class node attribute attr underscore accessor colon data comma colon next node, and def initialize parameter data at data equals data and then end the definition of the function. Now the node class has 2 attributes. Data contains the node's primary value, which is the first cell. For example, the string A, while the next underscore node contains the link to the next node in the list. We can use this class as follows. Node underscore 1 equals node dot new quote string once. Node underscore 2 equals node dot new quote string upon, and then node underscore etc. And then node underscore 1 after that until once upon until node underscore 4. After that, we define node underscore 1 that next underscore node equals to node underscore 2, and then node underscore 2 that next underscore node equals to node underscore 3. That's how we link the node 1 to 2 and 2 to 3, and then node underscore 3 that next underscore node equals to node underscore 4. That's how we connect this to create a coherent message once upon a time. With this code, we created a list of 4 nodes that serve as a list of containing the strings once upon a time. Note that in our implementation, the next underscore node refers to another node instance rather than an actual memory address number. So, instead of an actual memory address number, it's actually an instant of the class. So the effect, however, is the same. The nodes are likely dispersed throughout the computer's memory, and yet we can use the nodes link to string the list together. So it's the same. It's even if it's the different class, that will create a different memory or cells, and it will be dispersed throughout the memory. Now, going forward, then we're simply going to discuss each link as pointing to another node rather than to a specific memory address. Accordingly, we're going to use simplified diagrams to depict linked lists such as this. Once, and then the second cell pointing to the next node, and then pointing to the next node, etc. This reflects our Ruby implementation of the node class. In it, the data method returns the node's data, while the next underscore node method returns the next node in the list. In this context, the next underscore node method serves as the node's link. Again, this reflects our Ruby implementation of node class. In it, the data method returns the node's data. So the data method returns the node's data. So the data method we created, it will returns the node's data, which is the value, while the next underscore node method returns the next the next node in the list. In this context, the next underscore node method serve as the node's link to the next node or list item. While we've been able to create this linked list with the node class alone, we need an easy way to tell our program where the linked list begin. To do this, we'll create a linked list class in addition to our previous node class. Here's the linked list class in its basic form. Class linked list, and then without colon or anything, attr again underscore accessor colon first underscore node. Def initialize first underscore node, then at first underscore node equals first underscore node, and then end. We end this definition function inside this class, and then end the class. So at this point, all a linked list instance does is keep track of the first node of the list. Previously, we created a chain of nodes containing node underscore 1, node underscore 2, node underscore 3, and node underscore 4. We can now use our linked list class to reference this by writing the following code. List equals link list.new node underscore 1. So at this point, all a linked list instant does is keep track of the first node of the list. So this class only keeps track of the first node, which essentially what it needs to traverse all to that list items. Previously, we created a chain of node, which is a lot of code, right? Containing node underscore 1, node underscore 2, node underscore 3, and node underscore 4. We can now use our linked list class to reference this list by writing the following code. List equals to link list dot new node underscore 1, and the code or the traversal will take care of itself, kind of like a recursive top-down function. Now this list variable now acts as a handle on the linked list, as it is an instant of linked list that has an access to the list first node. A really important point emerges. When dealing with the linked list, we only have immediate access to its first node. This is going to have a serious ramification, as we'll shortly see. At first glance though, linked lists and arrays are pretty similar. They're both just lists of stuff. When we dig into the analysis, though, we'll see some pretty dramatic differences in these two data structure performance. Let's jump into 4 classic operations: reading, searching, insertion, and deletion. So reading, if you want to read, say, the value of the third item of a linked list, the computer cannot look it up in one step because it wouldn't immediately know where to find it in the computer's memory. After all, each node of a linked list could be anywhere in memory. All our program knows immediately is the memory address of the first node of the linked list. However, it doesn't know offhand where any of the other nodes are. It turns out then that if we were to read from the last node in the list, it would take n steps because we need to start with the first node. for n nodes in the list. Linked list having a worst case read of ON is a major disadvantage when compared with an arrays that can read any element in just O1. But don't fret, as linked lists have their own moment to shine, as we'll soon see. So let's go ahead and read a method to our linked list. Def read parameter index current underscore node equals to first node, current underscore index equals to 0. So we define the index and then the first underscore node. We begin at the first node of the list, and then we create a while loop on this function inside this def read. While current underscore index is less than index, do current underscore node equals to current underscore node dot next node, and current underscore index plus equals 1. So we change the value of the current underscore index and current underscore node inside this while current dot index that dash index less than index loop. So we keep that means we keep following the links of each node until we get to the index we're looking for, and then we return nil unless current underscore node. So if you're past the end of the list, that means the value cannot be found in the list, so we return nil, and then we end the while loop. And then after we end that while loop, if our code did not match that while loop, we return current underscore node dot data, which mean that we return what the data of that current. So that's how we read it, and then we end this read function. Now if you want to read the fourth node from a list, for example, we'd call our method by passing the node's index as follows: list.read 3. So let's walk through how this method works. First, we create a variable called current underscore node that refers to the node we're currently accessing. Since we're going to start by accessing the first node, we say current underscore node equals to first underscore node. Recall that first underscore node is an attribute of the linked list class. So we use that attribute of the linked list class here in this function of read. We also track the index of current underscore node so that we can know when we reach the desired index. We do this with current underscore index equals to 0 at first, as the first node's index 0. We then launch a loop that runs while current underscore index is less than the index we're attempting to read, while current underscore index is less than index do. So while it's less than the index we're attempting to read, so we then launch a loop by that. In each pass through of the loop, we access the node in the list and make it the new current underscore node. Current underscore node equals current underscore node dot next underscore node. We also bump up the current underscore index by 1, colon current underscore index plus equals 1. At the end of each pass through, we check whether we reach the end of the list, and we return nil if the index we're trying to read isn't in our list. Return nil unless current underscore node. This works because the final node of the list will actually have a next underscore node. That is nil, since last node was never assigned a next underscore node of its own. This is being the case when we call current underscore node equals current underscore node dot next underscore node on the last node. Current underscore node becomes nil. Finally, if we do break out the loop, it's because we reach the desired index. We can then return the node's value with return current underscore node dot data. So if you break out the loop, it means that we reach the desired index if we pass to that loop.